So, hello everyone. Today we will start the module 3 characterization of interfaces. So, the first lecture in this module is methods for surface tension measurements. So, before we will start this lecture, we will recap the module 2. So, in the module 2 we discussed about the surface tension, surface energy, then interfacial tension and interfacial energy. Also, we discussed the thermodynamics of the interfacial energy. Followed by that, in the next lecture, we saw what is the wettability or contact angle and how it is related with the Young's equation, how the wettability is related with the spreading phenomena, what is the effect of different chemical and physical heterogeneity on the wetting process, and then we just saw the contact angle hysteresis, which gives the information about the heterogeneity or some changes in the interfacial energy. In the last lecture, we discussed adhesion and cohesion. We also briefly discussed a few examples of adhesion in biological systems. Then we discussed the adhesion mechanisms based on the JKR and Hertz theory. So, JKR considers that interfacial layer is deformed, or you can say it considered the adhesion, while the Hertz theory considers there is no adhesion. Then similar to the contact angle hysteresis, we also discuss the adhesion hysteresis. So, in today's lecture, we will talk about the various methods for surface tension measurements. As you remember, the surface tension or surface energy is related to the work of adhesion, and work of adhesion is related to intermolecular forces or intermolecular interactions. So, that is the theoretical, but today we will discuss experimentally how we can measure the surface tension or interfacial tension. So, there are different methods like detachment method, shape of liquid drop method or the dynamic method. So, we will discuss what are the different experimental methods are available to determine the surface tension or interfacial tension. So, different surface tension measurement methods are classified in the three categories. First one is the detachment based method, second one is the shape of static drop based method, and third one is the dynamic methods. The detachment based method means it includes that you are having a liquid and you are contacting it with some objects, then you are detaching it, and once you are detaching it, then there will be some adhesion forces, or you can say some force will be required, and that force will be equivalent to the surface tension. So, different methods in this category are the drop weight. So, we are going to exactly monitor the weight of a drop. Then ring method, in this one we are going to bring a ring into the contact of the surface of a liquid, then we will pull out the ring and determine the surface tension. In this Wilhelmy slide method, apart from ring we are going to have a plate. Next method is the, if you can capture the shape of a static drop, then you can calculate the surface tension. So, we can have two different type of drop, one is the hanging drop, other is the drop on the surface or sessile drop. So, we will see the pendant drop method, sessile drop method, also we will see the spinning or rotating drop method. Apart from this, we will also briefly discuss about the various dynamic methods. So, which includes method in which we are having some sort of fluid flow. So, fluid flow means we will just see flow method, then we will see capillary waves and the maximum bubble pressure method. So, we will start with first detachment based methods. So, this detachment based method, as I told, we are going to put objects initially into contact with the liquid and gradually pulling away from the surface. So, if you put in the contact and pull away, so you require some additional force, and that force is exactly equivalent to the surface tension of that particular liquid. The surface tension of liquid, it means it is having some sort of cohesive or adhesive force at the interface, and that offers resistance force when we detach that particular object, and that resistance force is equivalent to the surface tension of that particular liquid. So, depending on the shape and size of the object being used for the detachment process, we call either a ring method or the plate method. So, very first one we will see the drop weight method. So, this is the old method being used for the measurement of surface tension at both the interface, liquid vapor and the liquid liquid interface. So, typically for the liquid vapor we call the surface tension, and for the liquid liquid we call the interfacial tension. So, the main theory or the principle behind this method is the maximum force to support the weight of a drop is contributed by the surface tension. So, if you can measure the weight of a particular drop, you should be able to calculate or estimate the surface tension. So, in this method we allow the drops from here to fall in the container, and we count the number of drops, how many number of drops is coming, because measurement of weight of one drop may not be very accurate. So, we consider the weight of drop until enough to accurately determine the weight per drop, and once the weight per drop is known, then we calculate the surface tension of the particular liquid. This method is also known as stoichiometric method or drop volume method, because we are going by the drop of a particular volume. Once the weight of a particular drop is known W, then we can calculate the surface tension using the Tate's law, which says that weight of drop is directly proportional to the surface tension. Here R is the capillary radius, and again you see there is a extra term called F. F is known as the error factor or the correction factor. So, if you just see what happens during the formation of a drop from a capillary tube, the weight of drop is increasing, and once the weight of drop is sufficient enough, then it detaches from the capillary. Now, if you see it is detaching from the here, but again there is some volume of the liquid is still attached to the capillary, and it is found that about 40% of drop volume is left at the tip of the tube. So, in that case the actual drop volume is lower than what it should be. So, that is why we can write W as a W dash, and here we are to consider this or to incorporate this error, we are adding a error factor, and as you know this error factor is coming from the what is the size of the capillary radius, as well as there is some leftover at the tip of that capillary. So, Harkins and Brown proposed the error factor as a function of r upon A. R is the size of capillary, A is the size of the drop, and as we know the A is a function of drop volume to the power 1 by 3. So, we can say this correction factor or error factor is a function of size of capillary divided by the size of that drop. So, the W weight of drop we can calculate simply by the W is equal to m into G, and for the F this is the table given. From here you have to see what is the ratio of R upon A. If you know the ratio of R upon A, it may vary from the 0.3 to 1.55, and correspondingly we have to choose the value of correction factor. So, value of the correction factor, if you see, it is varying between 0.55 to it is coming 0.73. So, this is the value of correction factor. So, it is very simple method. What it says, the formation of one drop is supported by the surface tension. So, the weight of one drop is directly proportional to the surface tension. So, if you can measure the weight of one drop, you should be able to calculate the surface tension. So, this is the weight of one drop divided by 2 pi, r is the capillary radius and F is the correction factor. Next method is the ring method. So, in this method what we are doing is, there is a liquid surface and we are putting a object, or you can say you are putting a ring. Typically that ring is called the Dunoyer ring. So, this is typically a ring like this, a ring, and then we are going to pull this ring, and if you pull this ring from the interface, there will be some sort of resistance offered by that liquid, and that resistance force will be equal to the surface tension. There is a ring here, this is a surface. Once you bring the ring into contact of the upper layer of the liquid, then you are pulling it out. So, the total weight will be the weight of ring plus surface tension or interfacial tension of particular liquid. So, interfacial tension into 4 pi r. 4 pi r is the its perimeter of the ring. So, this is very simple method based on the force balance, which says that if you are pulling the ring which is in the contact of the interface, so the force applied will be equal to the surface tension. So, if you are having a liquid here, this is the liquid, we have put the ring here and we are pulling it out. So, this phase is the liquid, this phase is the vapor. So, this is the liquid vapor interfacial tension. If you want to measure the surface tension of any pure liquid or pure benzene, toluene, so you can put and apply the ring to pull it out. But this method can also be used for the liquid interfacial tension. We are having the liquid 1 here and liquid 2 here, and at their interface we can bring the ring and we can pull it out. So, this method, ring method, can be used for the measurement of liquid vapor interfacial tension as well as the liquid interfacial tension. So, here again, as this ring is coming into contact of the liquid, if you pull it out, there will be some sort of liquid will be still attached on the surface of the ring. It will not be 100% detachment without any contact of liquid and the drop. So, whatever weight we are measuring, that weight will also include the some leftover fraction of that particular liquid. So, considering this, Harkins and Jordan proposed the correction factor, but here the correction factor will be the function of two parameters. One will be, of course, this is the radius of ring and the size of the, or you can say the thickness of the ring, and apart from that other will be the same as we discussed for the drop volume method, that will be the function of volume. So, volume function will be r q upon v and r upon r. So, r is the radius of the ring and small r is the thickness of the ring, and r v is the meniscus volume, and accordingly you have to take the r cube value, because at the meniscus this is the particular contact. So, we can say here the correction factor will be the function of two parameters r q upon v and r upon r, and you can simply say whatever the surface tension we are getting, and P is the ideal surface tension, and whatever we are measuring is coming because of the experimental error. So, if you multiply P with the correction factor, so that will be, it means gamma is equal to P ideal surface tension into correction factor. So, if you can calculate the correction factor, you should be able to calculate the ideal surface tension. So, this is the measured surface tension, this is the correction factor. So, you should be able to calculate the ideal surface tension. This is one typical instrument, or you can say experimental setup. So, here this is a bowl which is filled with the particular liquid, and what you are seeing, this is the ring. The ring is coming in the contact, and then instrument will pull it out, and once it is pulling it out, it will automatically measure the W total, and once it is measuring the W total, it will automatically calculate the surface tension. Typically, the material used for the ring, it should be inert, so that it should not interact either physically or chemically with that particular liquid. So, we use the platinum ring because it is a light as well as it is the inert, and this instrument is known as the tensiometer. So, the instrument which we are using to measure the surface tension, we call them as a tensiometer. So, apart from ring method, we can also use the other object which will come into contact of the liquid, that is like a plate. This is a liquid, you are having a plate here. So, that is known as the Wilhelmy slide method or Wilhelmy plate method. So, here we are having a thin plate, again the material of the plate, it should be inert and light. So, we mostly use the platinum materials. It is dipped perpendicular in the liquid, and once it is at the surface layer, we pull it out, and force experienced while the pulling it out is equivalent to the surface tension, and which is measured again by the either a microbalance or the tensiometer. So, W total will be the weight of the plate plus the additional weight is coming because of the surface tension. Surface tension into, of course, what is the perimeter of that particular plate which is being used for this experiment. So, once you pull the liquid out, you can see there is a formation of certain angle here. There is a formation of certain angle at which it is pulling it out, and if you consider this, the length is plate is L, then this perimeter will be twice, because both the side of the plate is coming into contact, twice L cos theta into the surface tension. So, the perimeter will be twice L cos theta, and 2 is coming because the plate is being contacted from the both the sides. So, the advantage of this method is this method does not require a consideration of the correction factor. This is the first advantage, and second advantage is the accuracy of this method is 0.1% if the liquids are wetting properly to the plate material. So, in these methods we take either the ring method or the plate method, the liquid should wet to the either the ring or the plate, then we are pulling it out and we are measuring the surface tension or the interfacial tension. So, what is the requirement for the material of the ring or plate is that it should be inert, it should not chemically interact with the liquid, also it should be of the lightweight as light as possible. So, we mostly use the platinum ring or the platinum plate, but again it should be perfectly horizontal. If this is not perfectly horizontal, then again the one part of the ring or plate will touch the liquid, other part will not touch the liquid. So, this is the liquid and your plate is not horizontal and you are pulling it out, then this is touching the liquid, this is not touching the liquid. So, again we are going to get some error in the results. So, the liquid same for the ring as well as for the plate. So, it should be perfectly horizontal, so that whole length of the plate or the whole perimeter of the ring should touch the interface and it pull it out. So, now we are going to analyze the shape of a static drop. As we understood, the formation of drop is regulated by the surface tension of the particular liquid. So, if we can form the small drop or the bubble, typically it tends to be the spherical. Why? Because the surface forces depends on the area. If it is spherical, then it is going to have, let us say this, there is sort of force is applying all the direction. So, if it is the spherical, it is going to minimize the contact. So, that is why they are coming through the intermolecular interactions, then it will form a particular well sphere, but again if there is some external force, as we know mostly the gravitational force will be there, then what will happen? It will not let it be perfect sphere, it will try to deform it. But the only thing is that this gravitational force depends on the mass, or you can say it depends on the volume of the liquid. That is why we are talking, you have to deal with the small drop or the small bubbles. So, there are two ways we can put a drop on the surface or the interface. One is the hanging drop, second is the sessile drop. So, this pendant drop, this is the sessile drop. So, this dimension of the drop under no disturbances. No disturbances means of course, the gravitational force will be there, but we will try to minimize it, but apart from that there should be no other external disturbance. And if you capture the shape of the static drop, then we calculate the surface tension. The first method is the pendant drop method. So, here the liquid is forming a pendant drop, it is coming downwards, it is forming a drop here. So, liquid drop is suspended in the medium. So, that medium may be another liquid or it may be the air. So, if it is the liquid, it will be the liquid interfacial tension. If it is the air, it will be the liquid vapor interfacial or tension or surface tension. So, as we discussed, the surface tension gives a spherical shape, while gravitational is responsible for the elongated shape, and the drop hanging from the tip grows in the size because of the hydrostatic pressure difference inside the drop as well as the external region of the drop, and because of this pressure difference we can calculate the surface tension using the Young's Laplace equation. So, which says Young's Laplace equation says surface tension is equal to delta P into R, but here we are having the delta P is the P internal and P external. So, why we are having inside and the external region? Because the drop is not spherical. So, if we take the middle point, so this is the R2, R2 is the radius at the middle point of the drop and R1 is the radius as the curvature. So, inside we are taking radius as the curvature and external means we are considering as a perfect sphere at the middle point of the drop. So, it is going to have two radius R1 and R2. So, using very simple Young's Laplace equation, if we can estimate the delta P and we can calculate delta P, then this R1 and R2 we can analyze from the shape of that particular static drop, then we easily estimate the surface tension. So, delta P we have to estimate the delta P and the R1 and R2 we have to estimate from the image of the static drop, then we calculate the surface tension or the interfacial tension. Next method is the sessile drop method. The earlier one was the hanging drop, here we are putting the drop on a surface. So, we put the small drop and its shape depends on the line tension along with the contact line. Okay. So, here again the surface tension is directly related to the what is the height of the particular drop on the surface H. Delta rho is the difference in the density and G is the gravitational force upon 2. So, in the hanging drop also if you measure the value of H, which we can analyze if you have captured the static drop, then we delta rho density difference is of 2 medium. If it is liquid air, then we have to take the density difference between liquid and air. If it is between liquid, then you have to see the density difference between two liquids, and G is the gravitational force. So, we can calculate the surface tension. Apart from the surface tension, this sessile drop is mostly used for the measuring the contact angle. That will be discussed for the contact angle measurement. So, whatever the contact, if you draw a tangent at the contact, so this is known as theta. So, if you having liquid drop like this, or you can say sessile drop like this, you draw a tangent here and this angle is the theta. That theta is known as the contact angle. So, this sessile drop method is also used to measure the contact angle. So, that we will discuss in the next class. So, next method is the rotating or spinning drop method. So, in this method you are having a horizontal tube which is filled with two immiscible liquids. So, mostly it is used for the measuring the liquid interfacial tension. It is having two immiscible liquids, but here there is a difference in density also. The density of B is higher than the density of A, means this is filled with the dense fluid and a drop of lighter liquid is put here or inserted here, then we rotate it. So, once we rotate it, the drop of a first forms a circle, then it reaches to the center here because of the centrifugal force. Then it again, if you continue rotating, it elongates, then it deforms to the ellipsoid, and finally it end up with a, this is a big cylinder, and the small drop is also forming a small cylindrical shape. So, if you capture again here the shape of that interface or shape of that particular drop of A, we should be able to calculate the, I estimate the liquid interfacial tension. So, that why this shape change is happening, because the liquid drop is experiencing both centrifugal force as well as the interfacial forces. So, because of this there is a deformation of the shape, and if you can capture the image of the static shape. So, as we told, there will be centrifugal force because which is coming because of the rotation, and of course, there will be the interfacial force between the two liquids, and this interfacial tension is related to the speed of rotation, difference in the density of the two liquids, and r is the drop radius. So, the drop radius r we have to analyze from the image, drop shape image, or you can say the drop shape. So, if you know what is the speed of rotation omega, difference in the density, what is the drop radius, then we can estimate the interfacial tension using the Vonnegut equation. So, this equation is also known as the Vonnegut equation. So, these were the three methods, hanging drop, sessile drop, and the rotating drop. Now, next we will see the dynamic methods. So, in dynamic methods, typically if there is a liquid, it is coming at the interface, there will be the adsorption at the interface, and if there is a adsorption, so we should be able to see some sort of the change, or you can see, you should be able to see some sort of the deformation at the interface, and the particular shape will be formed at interface because of the surface tension. So, if you can measure what is happening at the interface, we should be able to calculate or estimate the surface tension. So, especially if this is a dynamic method, so we require a advanced computer control devices to monitor what is happening at the interface in few millisecond to a scale of minute or so. So, we have, so particular these methods require the computer control devices to see or to monitor what is happening at the interface, at the whatever change is happening at interface is coming from the surface tension or the interfacial tension. The first method is the flow method. So, in the flow method what we are doing is, we are having a orifice, but this orifice is not circular. We can say it is like a elliptical jet, and if you flow that liquid, so this method is not suitable for the liquid air interface, but this is suitable for the liquid interface. So, if you flow the liquid, so what will happen? It is having the elliptical shape, it will go to the circular shape, then it will go to the horizontal elliptical shape, again it will go back to the circular, then it will go back to the its original elliptical shape. So, this is like a forming a particular wave or a particular cycle. So, starting from the elliptical, circular, then horizontal elliptical or cylindrical, then again circular, then elliptical. So, if you can capture this cycle, so lambda is the wavelength, we consider lambda is a wavelength here from change of one shape to the repeat of the same elliptical shape. And so, considering this initially started by the Rayleigh and finally, the Bohr mathematically proposed, we can calculate the surface tension or interfacial tension if we can monitor or observe this phenomena. So, it says 4 rho is the density, V is the volume velocity. So, there are two parameters we are playing with, one is the B and other is the R. So, R is the sum of the minimum and maximum half diameters. So, there are different half diameters. So, this is the sum of the minimum and maximum half diameter, and B is the differences between the minimum and maximum half diameter. So, these two parameters we have to analyze from these images, or you can say computer control devices, and once this B and R is known, in this equation we can easily calculate the surface tension. So, what we need is the B, R and lambda. So, if this is known, we can use the Bohr's equation or the model proposed by the Bohr to we can directly estimate the surface tension or interfacial tension. So, next method is the capillary wave. So, what it says is the if you are having a liquid in the other liquid or a drop of liquid into the deep body of the liquid. So, the wavelength of ripple on the surface or interfaces depends on the surface tension. So, it means the surface tension will decide what is the wavelength of the ripple at the interface if you are putting a drop into the another liquid. So, to see after seeing this phenomena, Kelvin mathematically proposed that the velocity of propagation of this capillary wave. So, we call this wave as a capillary wave is directly proportional to the wavelength as well as the interfacial tension. So, it says the velocity of propagation is sum of the is wavelength plus interfacial tension. So, we have to what you have to monitor is the wavelength, and once we know this wavelength we should be able to calculate the. So, we require this wavelength and this velocity. So, velocity we can also get from the tau period of the ripples, either velocity or tau. So, if you can estimate these parameters from this computer control devices, then you should be able to measure the interfacial tension by the model proposed by the Kelvin. So, it says if you just rearrange this, you should be able to get the density into wavelength ka cube divided by 2 pi into tau ka square minus g lambda ka square wavelength square density upon 4 pi square. So, here again we have to determine wavelength, period of the ripples as well as the r, the velocity of the propagation. Once this is known, we can estimate the surface tension. So, the next method is the maximum bubble pressure method. So, in the liquid we are going to form a bubble of, let us say, bubble of the air. So, what this method suggests is the, if there is a formation of the bubble, so the pressure required to form the bubble is related with the surface tension, or you can say the interfacial tension. So, dynamic surface tension measurement using the maximum bubble pressure method. So, what is the maximum pressure required to form a bubble, and its resolution, as I told this, it may be in the millisecond time frame. So, we require very advanced computer control devices. So, if you add the bubbles, there will be increase in the system volume relative to that of the bubble. So, if you can track the bubble formation frequency, in order to track the bubble formation frequency, we have to use some electrical or acoustic sensors. So, once the bubble formation is known, so you can see what is the maximum pressure required to form the bubble, and as well as we will see what is the size or the radius of the bubble. So, we should be able to calculate the surface tension and interfacial tension with the Young's Laplace equation. So, this technique is mostly used for the surfactant and the polymer solution, where there the adsorption of surfactant and polymer is taking at the interface. So, we will just see one example. So, here the ring tensiometer was used to determine the surface tension, and the diameter of the ring was 19 millimeter. So, with different time, what you see, with increase in the time, it is pulling and measuring the weight, but there is some decrease in the weight also. So, what does it mean? It is reaching to the equilibrium with time, and typically if you just see, it is starting from 0.92, it is going to 0.90908. So, it takes about 55 seconds, you can say, about the pulling process completes in the 1 minute, and then this is the constant. So, this is the, so this particular mass will give you the, what is the value of the surface tension of that particular liquid. So, if you remember how to calculate based on the ring method, so the surface tension will be m g upon, here capital R is given, so it will be 2 pi r. Let us consider f is equal to 1, because correction factor is not given here, let us consider correction factor as 1. So, this is the m is given 0.92, you multiply with the g 9.81, 2 pi r is given here, we can easily calculate the value of the surface tension. So, the surface tension, if you plot the value of surface tension versus time, it will be like this. So, it will start from here, and because of some equilibrium it will reach. So, this is the static or the equilibrium surface tension. So, if I calculate here, so based on this, its value will be coming around 75.7, and here it will reach to the 74.6 or something like that. So, we can easily calculate here what is the value of surface tension. So, it will be mass into g divided by 2 pi into the, what is the r of the ring, that is given, that is 19 millimeter. So, in this method the surface tension of water was measured, and if you just see, so there are two phenomena is happening. One is the pulling of the ring, then pushing of the ring. When it will push the ring, then again it will experience some resistance that is equal to the surface tension, as well as if it is pull, then again it will experience the almost similar surface tension or similar resistance that is equal to the surface tension. So, we can see the black dots are representing the during force required during the pulling, and the red dots are the during the pushing. So, what we are seeing, the same phenomena we are observing here, the surface tension in around 50 seconds or so it is coming to the static value. So, it is a dynamic process and it reaches to the equilibrium in about 50 to 60 seconds during the experiment. Here the surface tension of water we are measuring is about 70 point, the equilibrium area is coming 70.2. So, as I discussed, we are measuring experimentally the surface tension, and the surface tension depends on the work of adhesion and work of cohesion, and work of adhesion and work of cohesion is related with the intermolecular forces. So, now the surface tension is, as intermolecular forces vary with the temperature, then surface tension also depends on the temperature. So, if you are measuring experimentally also, the experiment should be performed at a constant temperature, and the measured or the estimated surface tension is reported as the observed interfacial tension at a particular temperature. So, here I conclude this lecture. So, we discussed three different methods to measure, experimentally measure the interfacial tension. The first one is the detachment weight method. So, in the detachment, first we saw if you want to detach a drop of the liquid. So, the rough shape of the drop of liquid is, you can say the formation of the drop is related with the surface tension of that liquid. Second method was that same formation of the drop as a pendant drop, and next was the sessile drop. So, if you can statically analyze the shape of the drop, either pendant drop or the sessile drop, or you can say the rotating drop, then we should be able to measure the interfacial tension. Also, we can apply some particular objects like a ring or the plate to estimate the surface tension. So, we discussed the Dunois, or you can say circular ring, as well as the plate, a thin plate, to measure the surface tension. And in the last, apart from that, if you are having some computer controlled devices, so we can use the dynamic method to measure the surface tension. So, that where the flow methods, capillary waves, are the maximum bubble pressure method. So, here I conclude this lecture. Thank you.